Dear delegates, my dear Turkish friends, how much would I like to be with you today and share this wonderful experience and time to discuss at the CUSCIT conference. But unfortunately, it is impossible for me today to travel, so I want to convey my message to you through this channel. CUSCIT has developed to be a major event in the Turkish cement industry. Top executives, decision makers, and renowned experts from the Turkish industry are gathering to share their knowledge and their experience and to discuss the most pressing issues of their industry. But not only from Turkey, delegates have registered for this conference, but also from other European and regional countries and as well from overseas. I wish all delegates 2 days of interesting talks, interesting and fruitful discussions, and a good time at the CUSCIT conference. Ladies and gentlemen, we all know and we feel that times are challenging like they have never been before. The cement industry is amidst this transformation into a digitized and decarbonized future. And what sounds like a positive development and something that we should long for, in reality comes to us as a major decision-making problem. There are so many uncertainties and so many questions open at this time. We know we have to do something, but what? Which technologies will prevail? Which technologies do we have to use to go into decarbonized future? Which technologies still have to be developed? How should we finance all this? What is the future of cement anyway? As we know, the production of cement is responsible for 8% of the total man-made CO2 emissions. That's a huge bunch. But the question is, are there alternative materials which we could use, which will have a smaller CO2 footprint? Cyril Diment from Cambridge University has put together data of cement and concrete and alternative building materials and put them into a diagram regarding their CO2 relevance. In this diagram you see on the horizontal axis the energy embodiment of the building materials, and on the vertical axis you see the embodied carbon itself. So the material with the lowest CO2 footprint will be on the lower left-hand side of the diagram, and the material with the highest CO2 footprint will be on the upper right-hand side of the diagram. And surprisingly for some, you will see that cement and concrete are the most eco-friendly materials of all the alternatives. You see steel far up right, you see timber far up to the right, and concrete actually is the material with the least carbon footprint. It's the most eco-friendly material. Just recently, Karen Scrivener has published data which tell the same story. She has found out that cement and concrete, related to its weight, have only 1/4 of the CO2 footprint of timber and only 1/13 of that of steel. So again, we see that concrete and cement are the most eco-friendly materials we have. The huge emission of CO2 of cement and concrete manufacture comes only because we produce such a mass of material, more than 4 gigatons per year. If we would use different materials, the CO2 emission would even be higher. Now, some people name timber specifically to substitute cement and concrete. That is true to a certain extent, but only limited extent. Timber is not able to substitute cement in big infrastructure projects like bridges, dams, airports. sewer systems, or very tall buildings. Timber may take some 10% of cement and concrete, but not more. And if we would use more timber, we would cut all the trees, and then we would miss the ability of the trees to capture CO2 out of the air. So we need forests and trees to grow and make photosynthesis. So there's only a very small amount of timber to replace cement and concrete. And as we've seen, the other building materials are having a still higher CO2 footprint. We can safely say that cement and concrete are indispensable. Whenever societies grow, whenever infrastructure projects are being made, cement and concrete is the material of choice with the lowest possible CO2 footprint. So if cement and concrete are the most eco-friendly materials, what will be the amount of cement and concrete we are going to need, we are going to produce in the future? There are lots of estimations, and they come to quite different results. Let me try to walk you through some of the numbers and figures of the several studies which are out there. Let's start with the voice of the UN, with Antonio Guterres. He is known to have said the statement, 3/4 of the infrastructure that we will have in 2050 still has to be built. And you may also recall a famous saying that we are going to have to build another New York City every day. So these are alluding to high numbers. What does it mean in actual numbers? Now, the journal Nature has published recently an estimation that up to 2020, the world has installed approximately 550 gigatons of concrete. If we now take Antonio Guterres by word and estimate what it means that we'll have to build another 3/4 by 2050, this would mean we'll have to add another 1,650 gigatons of concrete by 2050. This would mean, in the 25 years to come to an annual production of 65 gigatons of concrete per year for the next 25 years. That is approximately more than double of what we produce today. So we see that that's a huge amount of concrete to be built in the future. Certainly, we'll have to double check these data, and certainly also the UN is assuming certain societal development projects which are heavily influencing the production of concrete and the need of concrete for the development of certain societies, and maybe not all of those projects that the UN is following will come true. But definitely, we'll have to expect high demand in concrete for infrastructure projects. Think alone of what happens if the sea level is rising due to climate change, and all the big metropolises at seaside will have to be protected by dams or have to move inland. Think of Istanbul, New York, Sydney, Amsterdam, Kuala Lumpur, Jakarta, Mumbai. All those big cities will have to be protected against the rising sea level, and that is going to consume a lot of concrete. But there are also estimations around, for example, from the GCCA, the Global Cement and Concrete Association. This organization claims to represent 80% of the worldwide cement production. And of course, they have also made some estimations, and they estimate that the concrete growth to 2050 is 143%. They estimate that they can reduce some of that amount by binder optimization, less cement in concrete, a small share of alternative binders, and massively by reducing the clinker to cement ratio from presently 0.65 down to 0.52. This all translates into a reduction of clinker production by 2050 of -40%. So these are the numbers of the concrete demand and estimations for clinker production. And of course, you see that the concrete demand is rising and the clinker production is falling, which means in the concrete recipe and in the cement recipe, we have to substitute clinker by cementitious supplementary materials. And we can take, as we do for a long time already, fly ash and slags, but fly ash and slags are going to decrease in their availability in the course of the transformation process of the power industry and the steel industry. So there will not be enough fly ash and slags to put into our concrete and cement. So the only material in the world that is available everywhere and available in sufficient masses is clay. With the right type of clay and the right process technology for producing calcined clay can substitute up to 50% of clinker in cement. Now, of course, in this multi-billion business of transforming the cement and concrete industry, you can believe that there are multiple studies around and other associations, research institutes, and consulting companies come up with their estimations. So you see there's a high amount of uncertainty in the projections for the cement demand and the clinker demand in 2050. But we can take the average information of all these studies and projections, and I think we can agree on the following. It is very hard to make such prediction at this moment with the high amount of uncertainties we have. But we have to assume that clinker production will see a major reduction in the future, and at the same time with growing concrete demand, we have to drastically increase the production of calcined clay. The activities of our industry are far behind what is necessary in order to reach the targets of the Paris Agreement and to reach net zero and carbon neutrality by 2050. Based on the average assumptions of clinker and concrete demand, however, we know that concrete and cement will remain indispensable for the societies as long as we will be building infrastructure and as long as we will be building buildings, we will need cement and concrete. There is no prosperous future without concrete. But we'll have to change the type of concretes. We have to change the type of cements. And we need to decarbonize the cement and the concrete industry. The time to act is now. The European Environmental Agency, EAA, an institution of the European Union, has just recently published a report in which they clearly state that the activities for decarbonization fall sharp below what is necessary to achieve carbon neutrality by 2050. Likewise, the advisory board of the German government has just recently published that the available budget to spend CO2 by trying to achieve the Paris Agreement and carbon neutrality by 2050 is going to be used up in Germany by 2033. That is only 8 years from now. From then onwards, Germany would have to be carbon neutral in order to reach the Paris Agreement targets. That is a bunch. And even though the cement industry in Germany makes up only 2% of the carbon emissions, it shows that the whole industry, and specifically the heavy industries, are far behind the target, which they would have to achieve in order to be carbon neutral in 2050. The reason for this procrastination they see in overboarding bureaucracy uncertainties in financing and uncertainties in carbon cost in the future. And also the carbon border adjustment mechanism, the CBAM, is not really defined to all details, which makes it very hard for cement producers to calculate their carbon cost in the future. So this pretty much boils down to the question whether the international community will stick to the Paris Agreement or do they let it drop? It is hard for me to believe that a country, a state, which has signed the Paris Agreement can just drop out. It's only the USA. They do it at this moment, but the other 198 states or 197 states will have a hard time to drop out of the Paris Agreement. In turn, this means we'll have to decarbonize. Even though we might not believe that we can afford to do the investments, we'll have to do it. At KHD, we assume that the Paris Agreement will not get bust, and that the decarbonization targets will have to be materialized. 197 states are deeply anchored into the Paris Agreement, and we believe they will not let it drop. That's why we have taken a strategical decision at KHD to stay inside the cement industry. Unlike others who are leaving the cement industry, we stay in the cement industry because we believe there's a future for cement. There's a future for clinker, there's a future for calcined clay, and there's a future also for KHD in the cement industry. Therefore, we have concentrated all our efforts in a strategy slogan under the term Cement Beyond Carbon. Cement Beyond Carbon is a statement. It's a statement for the possibility to decarbonize the cement industry. It's a statement for the future of cement. Cement will prevail. But this Cement Beyond Carbon is also a promise. It's a promise that KHD will deliver the technologies, the machines and the equipment and the processes that the cement producers need to follow their transformation into the decarbonized future. We see the decarbonization of the cement industry happening in two steps, two phases. The first phase will be the reduction of CO2 emission. There are several ways to do that, and the biggest lever, we agree with the estimation of the GCCA, is to drastically reduce the amount of clinker in cement. This means we have to produce a big amount of calcined clay. Calcined clay is available all over the world in different forms and different types, but with the right processing technology and with the right engineering, it is possible to replace up to 50% of clinker with calcined clay in cement without losing its strength. Therefore, KHD has developed a highly efficient flash calciner technology which allows to control the retention time and the temperature of the clay so that we achieve an optimum product and the lowest possible energy consumption. Thereby, we can reduce the CO2 footprint of the cement production drastically. This picture shows the temperature curves of certain different types of clay. In our projects, we often hear that people have a hard time to find the right deposit for their calcined clay. Everybody's looking for kaolin, because kaolin is the highest quality clay or easiest to calcine. But as you can see in this picture, also different type of clays like muscovitic, montmorillonitic, palygoscitic and chloritic clays can be used to produce an amorphous, high-quality binder, You just have to put the temperature at the right position and the retention time. This is possible with the KHD flash calciner design. The flash calciner is fed with a very finely ground, homogeneous powder that is being created in an impact hammer mill and flows evenly through the flash calciner. This guarantees a controlled retention time and a controlled temperature. We have to avoid excessive temperature exposure because that increases recrystallization in the product, and we have to stick to the right retention time in the reactor, also to avoid agglomerates at long retention time and high temperature. This is what usually happens in a rotary kiln, where the temperature exposure is dependent on where exactly in the rotary kiln the particle moves. In the flash calciner, everything is homogeneous, temperature is controlled, not too high temperature, right retention time. Also, decarbonization or reduction of CO2 emission can be achieved by using alternative fuels. Substitution of fossil fuels is something that the cement industry is pursuing since many decades already, and KHD has a long-spanning experience in that. We have generated solutions for substitution of fossil fuels from anything between 10 to 99%. Especially our Pyrorotor, an external gasification chamber, is able to substitute up to 95% of the calciner fuel with coarse solid fuels or biogenic fuels, hard to burn, which need a long retention time, and the Pyrorotor flat material does not need any expensive pre-processing. So this Pyrorotor technology has been installed meanwhile 15 times around the world, and the operation experience is excellent, and the clients are using low pre-processed cheap alternative fuel to fire their calciner. Another option to reduce the CO2 emission is through generally optimized plants, most energy efficient plants. KHD is proud to have been pioneering this approach ever since, and all our plants are designed for optimum efficiency. We have invented the cyclone preheater, the flash calciner, the two-station kiln, everything to increase the efficiency of the process. But beyond that, we also have developed our ProMax RTO, which is a software system, an advanced control system that optimizes the production of the cement and clinker online with a combination of artificial intelligence and experience-based human intelligence. This system utilizes multiple neural nets being taught online on the plant and hedged by experience-based human knowledge to achieve permanent self-training, optimized production operation of the cement kiln. A next lever to reduce carbon emissions, of course, comes with the educational level of the plant operators. Therefore, we have developed our Simulex training simulator, which is on the market already for decades, and the renowned German Cement Manufacturers Association, VDZ, is using this simulator since decades already for their certified training programs. So we can safely say this is tried and true, and Simulex covers the whole clinker production, cement production process, from raw material to clinker silos or cement silos. Simulex incorporates a complete user interface with all the signals and all the alarms, the analogs and the digital signals incorporated like in a real control room. And Simulex operates at real time, so that trainees can learn how problems develop in real time and act on them. We have now developed this Simulex further to incorporate also a three-dimensional virtual reality experience, so that the trainees can walk through the plant in virtual reality, find out where the problem is, solve the problem, and return back to the control room and bring up the process again to its optimum operation. We have prepared, in connection with the CUSCIT organizers, Simulator Challenge in our digital experience room, which we have at this conference, and I invite everybody to come and take part of this in this challenge, where you will be presented some operational problem, you'll have to solve it, and the best trainees, the best operators which solve the problem fastest will be awarded a certificate at the end of the conference. Now, the second phase of decarbonization is what is coming when we will have reduced our CO2 emissions as much as possible. The remaining CO2 emissions are unavoidable emissions from the decarbonization of limestone, and they have to be captured in order to be carbon neutral. There is no way around. Even if we think it is much too expensive today, when we get to that point to become carbon neutral, we'll have to capture it. There are lots of technologies around today available, and everybody speaks about amine scrubbing, which is possible, which is available, which is expensive. There will be other technologies in the phase of development, some close to practical reality, some far away. Oxyfuel, for example, partial and full oxyfuel, is a technology which we deliver, which concentrates the CO2 in the off gas and makes the capture more easy and less expensive. But also other technologies are being discussed and developed: membrane technology, metal organic frameworks, mineralization, many technologies under development. And our role as KHD is to engineer a cement plant which optimally incorporates these technologies with the optimum process and with the highest efficiency. Ladies and gentlemen, I would like to close my speech with an appeal to us all. First of all, let's believe cement has a future, but it needs to be decarbonized. It's on us to act, and we have to act now.